Okay, here's the third video on equilibrium and equilibrium type calculations. What you'll find, last time we went through when you manipulate an equation, if you flip an equation, you take the reciprocal of k, you can add two reactions together. If you add them together, you multiply the two values of k. Now, types of problems you'll be getting concerning equilibrium. Probably the most common problem would be this type here. Given an equilibrium constant, given the concentration of species in a reaction mixture, figure out if the mixture is at equilibrium or not. And if it's not at equilibrium, which way is it going to go to reach equilibrium? Actually, that's not the most common, but that's one of the more common problems you'll find. So let's do a quick example. Let's say you have this equilibrium reaction here. You have hydrogen reacting with iodine to produce hydrogen iodide. And you're given the equilibrium constant K is 54. And you are told that you have a flask full of these three things. So you have a flask that contains all three of these, and these are the partial pressures. Again, a partial pressure is directly related to a concentration. You can express the concentration in terms of partial pressure. So, is the reaction at equilibrium? Yes or no? If it's not at equilibrium, to get to equilibrium, will the forward reaction proceed or will the reverse reaction take over? So, how do you go about doing this? You write your equilibrium expression or your reaction quotient expression, if you will, in this case, Q. The Q reaction quotient is the partial pressure of the HI to the second power, because of that 2. Numbers products over reactants, so it's that times the partial pressure of your hydrogen and the partial pressure of your iodine. That's your expression there. Now, hey, we've got a partial pressure for the hydrogen. We've got a partial pressure for the iodine. We have a partial pressure for the HI. Hey, you can just plug those numbers in and calculate a value for Q. In this case, plugging everything in, you'll get HI is 0.15 atmospheres. For the hydrogen, we got 1.98 atmospheres. The partial pressure of the I2 is the 0.24. Crunch out a number here, and the reaction quotient is 0.047. K for the reaction is 54. So, are we at equilibrium? No. When are you at equilibrium? When the value of Q equals the value of K, then you're at equilibrium. Then the concentrations stop changing. So right now, this reaction is not at equilibrium. So is it at equilibrium? No, it's not at equilibrium. Now, it's going to try to get to equilibrium. One of the big principles in the sciences is everything's kind of racing towards an equilibrium. Well, not necessarily racing, but everything wants to reach equilibrium. So this reaction is going to continue until I get some set of concentrations that plug into this whole thing, some set of concentrations that I can plug into this, where the numbers all combined end up giving us 54. So let's see, right now it's 0.047. Hey, this number wants to go up, right? How can I make that number bigger? If I make this term larger, so I make more HI, that's going to make that value go up. So in order to get to equilibrium, the reaction is going to proceed to the right. So the reaction proceeds to the right, makes more HI in order to reach equilibrium. So the forward reaction is going to predominate. Now always keep in mind, even once you hit equilibrium, the forward reaction is taking place, the reverse reaction is taking place. They just take place at equal rates. So if I'm making HI just as quickly as I'm destroying the HI, nothing changes in terms of concentration. Are the forward and reverse reactions happening? You bet they are. They're just happening at equal rates. Quick little trick with these, if you're ever wondering which way is a reaction going to go to reach equilibrium, your best way of doing it is probably to look at your numbers and say, okay, let's say I want this number to get bigger. I want this number to hit this, then I'm at equilibrium. How does this number get bigger if this number? The other trick, if you make a little table of K versus Q, and do it alphabetically. So put K first, Q second. So if you do K versus Q, and you put the numbers you got here, K is 54, Q for this reaction is 0.047. Put the greater than less than sign in here. Oh, yeah. Guess what? That little symbol's pointing in the direction in which the reaction has to proceed. So if you make a little table with K versus Q, and you list K first, Q second, put your numbers in it, your greater than or less than symbol will point in the correct direction. So again, this reaction, in order to reach equilibrium, the forward reaction is going to be going faster than the reverse. In other words, the reaction is going to be proceeding to the right until it hits equilibrium. Then there's going to be no change in the concentrations because the forward and the reverse reactions are taking place at equal rates. So that's one type of problem. Now, here's the more common type. This is actually the most common type of equilibrium problem you're going to encounter. This is where you are given a value for K. So you know what the value of K is. You're given a set of initial concentrations. And you're asked to find the equilibrium concentrations in the mixture. Now, these types of problems, the easiest way to work them is to make what's called a reaction table. Sometimes these are called ICE tables, because you're going to make a table. You're going to use the reaction itself as the top row for your table. Then you're going to have a row where you indicate the initial concentration of everything. We'll call that I. You're going to have a row that indicates the concentration, the change in concentration. You can say C for change. Some people for change in concentration will use a little triangle. Throughout the sciences, every time you see that little delta symbol, it means change. I'll use C for change. You're going to have a row in this table indicating the equilibrium concentrations of everything. So that's a reaction table. So let's go ahead and do an example here. This one says the equilibrium constant for the following reaction is 50. All right, we got the value of Q. If you start the reaction with 0.4 molar concentration of HI, so the concentration of this stuff is 0.40. What are the equilibrium concentrations of all the species in solution? So what's going to be the concentration of this, this, and this? So that's the information it's given us. Now, we started with this. Nothing's happened yet. If nothing has happened, the reaction hasn't really done anything yet. What's the concentration of hydrogen? 0. What's the concentration of iodine? I2. 0. Here's the part of making an ice table that some people struggle with, but it's really quite simple. How do the concentrations change? Well, as this stuff turns into these other things, its concentration drops, right? As this stuff reacts, its concentration is going to go down. So whatever you put here better have a negative symbol in it. Anything on this side of the arrow gets a negative symbol. Anything on this side of the arrow gets a positive symbol. You indicate how much it changes by using our favorite variable from algebra, x. So as this reaction proceeds, for every one of these that turns into this stuff, I lose 2. For every 2 of these, I make 1 of these. Anyway, keep it simple. It changes by negative 2x. Where the hell did the 2 come from? Right there. Don't fight it, guys. If this were a 3, this would be negative 3x. If this is a 5, negative 5x. It's that simple. How does the concentration of hydrogen change? It goes up by x. The concentration of the iodine goes up by x. What are the equilibrium concentrations? Hey, start with this, it changes by this much. Oh, the equilibrium concentration. I always put my equilibrium things in brackets. Makes it easier for me. It's going to be 0.40 minus 2x. The equilibrium concentration of hydrogen is simply going to be x of iodine is x. That's making an ice table. So you list what you start with. You indicate how things change using x, and the coefficient has to go in front of that x. If it's a reactant, it's a negative x. If it's a product, it's a positive x. So there's your ice table. Now that you have that, you write out your equilibrium expression. Oh, if you're ever lost in equilibrium land, doing some equilibrium work and you just don't know what's going on with the problem, 2 things you should always try and do. Make an ice table. The next thing you should do is write out your equilibrium expression. So your equilibrium expression for this reaction would be, again, the products over the reactants. So you'd say K is going to be the concentration of I2. And I'm using brackets because this gives us the concentration in terms of molarity. The concentration of I2, the concentration of the H2 by reactants HI, so it's going to be the concentration of the HI raised to what power? Oh, the second power. So that's my equilibrium expression right there. Now, I've got stuff I can plug into this here thing. You see where this is going, I hope. You're going to solve for x. So plugging everything in, the value of K is 50. The equilibrium concentration of I2 is x. See, here's my equilibrium concentrations. So it's going to be 50 x. Equilibrium concentration of hydrogen is x. I need the equilibrium concentration of HI. Oh, 0.40 minus 2x. What do I got to do to that? I got to square it. Hey, that's an algebraic expression. I can solve for x. And what does X represent? Oh, X is going to be the equilibrium concentration of iodine. X is also going to be the equilibrium concentration of this stuff. The equilibrium concentration of the HI is going to be 0.4 minus 2 times X. So to solve this, all I have to do is solve for X. This is where equilibrium problems get a little bit ugly, guys. What you're looking at here, you might not realize it, but from algebra, this has the form of a quadratic equation. If we rewrite this, it's going to be X squared all over 0.40 minus 2X squared. So anytime you have an algebraic expression where one term has X to the second power and the other term has a number minus X, it's a quadratic equation. They can be a pain to solve. However, this one's not so hard. This one takes the form of what you would call a perfect square, because your top term here is squared. Your bottom term, the entire bottom term, is squared. So this is the same thing as having quantity X all over 0.40 minus 2X squared. So again, if you get something like that, you have your number that you know is equal to your stuff with X. Oh, guess what? You can take the square root of this side on your calculator. Taking the square root of 50, your calculator is going to tell you it's 7.07. So what you want to do here is take the square root of both sides. 50 becomes 7.07. Well, how do you take the square root of this? Oh, easy. You erase that. That's the square root. So the square root of this side is X over 0.40 minus 2X. There's no more squares in there. It's not a quadratic anymore. It's pretty easy to solve. From this point on, it's straightforward algebra. So what you want to do here is, move this up a little bit. To solve this one, you're going to want to multiply this by the bottom half of this. So 7.07 times all of this. You'll get 2.828 minus 14.14 X is equal to X. The reason you're doing that, you want to get rid of this bottom half here, so if you multiply it, this whole side of the equation, by this denominator, that denominator goes away, and I'm left with X. So if I multiply this half, I got to multiply this side. So, and from here, it's pretty easy to figure that out. X, if you go through the algebra, here is going to end up being 0.187. So that tells you, back to the problem, that value of X is the partial pressure of the I2. That value of X is the partial pressure of the H2. So at equilibrium, I want to say at equilibrium, they're not partial pressures, I'm sorry, they're molarities. Iodine concentration is 0.187. The hydrogen concentration, 0.187. At equilibrium, the HI concentration at equilibrium, okay, equilibrium, your HI concentration is 0.4 minus 2x. So it's going to be 0.4 minus 2x, which is 0.4 minus 2 times 0.187. And your equilibrium concentration there is going to be 0.026. So these types of problems are pretty common. And again, these are ones where you're given an initial set of conditions, an initial set of concentrations. You know your value of K, and you want to predict the future. You want to predict what are the concentrations going to be once everything stops reacting and comes to equilibrium. And the way to do it, you make an ice table, you set up your equilibrium expression, you plug everything in, and you solve it for X. Now, if you want more practice with these types of problems, the very next page here, this very next blank page I give you, it's a, not blank page, but dang near blank page. It's the same type of problem. So, it's telling you have this reaction here, gives you the value of K. You're starting it with partial pressures of carbon dioxide and hydrogen of 1. And I'm not going to walk you through this whole thing, but in terms of starting it off, you make your ice table. So you're going to have the initial concentration, the change in concentration, the equilibrium concentration. You're going to have CO2 plus H2 reacting to give CO and H2O. When you set up this ice table, you start with partial pressures of carbon dioxide and hydrogen at 1 atmosphere. I'm going to leave off the units, but these guys start off at 1 atmosphere. Before anything's reacted, what's the concentration of these guys? 0. How did the concentrations change? These go down by X. These go up by X. At equilibrium, you'll have 1 minus X as your equilibrium concentration of carbon dioxide. 1 minus X as your equilibrium concentration of hydrogen. You'll have just X as your concentration of CO, and at equilibrium you'll have X as your concentration of H2O. I'm not going to walk you through all the math. Now the notes I sent out with that first video, that packet of notes, has this one all worked out for you. So if you wanted to see how the solution is going to look, it's in that packet of notes that I sent you. And yeah, so that's a very common type of equilibrium problem. You'll see it in the quiz, you'll see it in the midterm, these types of problems. Any problem like this that we give you, we're going to set it up to be a perfect square, like that last one we worked. We worked this one just a moment ago. And anything we give you on an exam, or the midterm exam or the final, it's going to be set up as something squared all over some other quantity squared, so that it's real easy to solve it. You take the square root of both sides. Again, taking the square root of 50, you can do that on your calculator. Taking the square root of this whole mess simply means get rid of that 2, and you've taken the square root. So the ones we tend to give you are ones that involve perfect squares. Now, there's uglier ones. I should walk you through this in my notes. You know, you're not going to see one of these on a test. Let's say you had one like this. let's say it's this reaction, the dissociation of dinitrogen tetroxide to give you NO2. And you start the reaction with 1 atmosphere of this stuff. So your initial concentration of N2O4 is 1 atmosphere. Nothing's happened yet, so he's got a concentration of 0. This goes down by X. This one goes up by 2X. At equilibrium, you've got 1 minus X. This one at equilibrium, you've got 2X. And you go to set up your equilibrium expression. You'd say your equilibrium expression for this will have K equals, oh, these ones are atmosphere, so they're partial pressures. So it's going to be the partial pressure of your N2O4 all over the partial pressure of your NO2 to the second power. Plugging everything in. Got that upside down, don't I? Should be the partial pressure of the NO2 squared. It's always products on top, reactants on the bottom. Partial pressure of your N2O4 to the first power on the bottom. Plugging everything in, partial pressure of the NO2 is a 2x, so we'll have 2x squared. On the bottom there we have 1 minus x, and that's a quadratic equation, and darn it, it's not the so-called perfect square. Now, I'm not going to bore us to death and chew up YouTube time here with this, but to solve this, you gotta, well, we need the number for k. K happens to be 11. So you want to solve this thing for x. Basically, you have to play around with this until you get it to look like this. And then you play around with it some more, get the equation to equal 0. So you play around with it so that everything adds up to 0. And at that point, you apply the quadratic formula, which is this. And in the quadratic formula here, basically, the value of a here is 4, because the value of a is the thing in front of the x squared. That is, the number in front of x is b, so b is 11. The other guy is c, so c is negative 11. You take these, plug them into here, you'll get 2 solutions. Now these problems are odd in that you solve it for x, you get 2 values for x. It turns out only one of these values makes any chemical sense. I can't have x being equal to negative 3.5. That would tell me that the equilibrium concentration of this stuff is negative 6 or negative 7 or something like that. 2 times negative 3.5. That's a negative 7. No, it can't have that. So this root, that solution to the quadratic equation, is meaningless, and this is the correct one. Guys, we will not have you work one of these that involve the quadratic equation during the midterm or the final. It's not a math class, but just so you know, these problems get really ugly really fast. You can get some nasty, nasty problems with these. So anyway, you're given value of the equilibrium constant, you're given an initial set of conditions, and you have to find the final set. What do? You make your table. You make your ice table. You set up your equilibrium expressions. You solve for x. Trust me, the ones that we give you where you solve for x will be a lot simpler than those. Last type of equilibrium problem. These ones are actually some of the easier ones. You're given equilibrium concentrations, and you're asked, what's the value of K? You'll be doing this in the lab if you haven't already, the laboratory portion of the course. So let's say you have this reaction. Two IBR react to give you an I2 and a BR2. And at a certain temperature, they let it come to equilibrium. After it hits equilibrium, you get the partial pressure of the bromine, the partial pressure of the iodine are each equal to 0.33. The partial pressure of the IBR is this. What's the value? Oh, geez, this is so easy. K is going to be the partial pressure of the BR2 times the partial pressure of the I2 all over the partial pressure of the IBR squared. Plugging in the numbers, piece of cake, it tells you the BR2, oh, it's going to be 0.33 times 0.33 all over 1.5 10 to the minus fourth. Squared. Crunch out the numbers there, and you'll have your solution on that one. Not much to that type of problem. Those guys are some of the easier problems you'll find. Looking for where I actually crunched them out there. Well, if you put these through your calculator, you'll get the value for K on that. Now, these problems can get just a teeny bit tougher. What if we don't give you all three values? We give you two of them. You have to find the third value using stoichiometry. And the easiest way to do that, guys, is to apply one of those ice tables. So let me show you how to do that. Let's say you're doing this same reaction, IBR to I2 to BR2, so you have 2 IBR reacting to give you I2 plus BR2. And you start the reaction with the partial pressure of the IBR being 2. So we're making a nice table. He's initially at a concentration of 2 atmospheres. Concentrations change. They hit some kind of equilibrium concentration. Before anything's happened, he's at 0. He's at 0. It's going to go down by 2x. This is going to go up by x. Up by x. This is going to be a lot simpler than you think, guys. 2 minus 2x. This guy is going to end up being x. This guy is going to end up being x. That's your ice table, but we don't have to solve for x. Read the problem again. You start with an initial partial pressure of 2 atmospheres. At equilibrium, the partial pressure of BR2 is found to be 0.2. Hey, guess what? This guy is 0.2, which means this guy is 0.2. Which means at equilibrium it's going to be 2 minus 2 times 0.2. X there is 0.2. Should all be in brackets there. You don't have to solve for x. It says at equilibrium the partial pressure is this. That's your value of x. You've been given the value of x. To solve for the k, value of k, with this whole system here, k is going to be the partial pressure of BR2 times the partial pressure of your I2 all over the partial pressure of your IBR to the second power. Hey guys, what are you going to plug in here for I2? 0.2. For BR2, 0.2. For IBR, you know, 2 minus 0.4. I guess that's going to be 1.6. So you're going to have 0.2 all over 1.6 squared. Run the numbers on that, you'll get your value of K. So again, that's doing stoichiometry with these ice tables. You weren't solving for X. Just set up the ice table. It helps you kind of see what's happening, and you're there. One last thing to talk about then, and I've been getting some mail about this, and that is a topic my notes kind of skip entirely, and that is KP versus KC. What the heck's going on with this stuff? Well, it turns out equilibrium constants, K, you get different values for the equilibrium constant if you're expressing the concentrations in terms of molarity. So Kc is what you get if you use molarity. Kp is what you get if you use partial pressures for your concentrations. So you get a different numerical value if you're expressing concentration in molarity than if you express concentration with partial pressure. So your book goes through a big mathematical derivation which you can skip. All you got to know is this equation here. Kp is equal to Kc times the gas constant R, and for the gas constant simply use 0.0821. Now you might recall it has some weird units. It's 0.0821 liters times atmospheres per mole. Forget the units. Don't tell anybody I said to do that. They'll take away my license to teach science if I say forget the units. But your value of R is simply this number. T is the temperature given in Kelvin. Delta N, that's the change in the moles of gas between the products and the reactants. So it's going to be moles of gas in the product minus moles of gas in the reactants. Quick example here. Oh, by the way, this equation is the same as this one. It's just been rearranged. So if you're looking for Kp, you want this equation. If you're looking for Kc, then you want this equation. So we've got our example here. This reaction, this is methanol. Methanol as a gas. Get it real hot. It can turn into carbon monoxide and hydrogen gas. Gives you a value of Kc at 500 Kelvin, or 277 C. You don't need this. Temperature in Kelvin. Find the value of Kp. Oh, okay. Well, that equation right above says Kp equals Kc times RT, your delta N. The delta N here, moles of gas in the reactants or products minus hey, in my products I have 1, 2, 3 moles of gas. Starting materials, 1 mole of gas. So 3 moles of gas minus 1 mole of gas. Delta N is 2. So plugging all that stuff in here, you get Kp would be your 0.0952, 0.0952 times R, 0.0821, times the temperature, which we said was 500 K. All that raised to the second power. And if you run all that through your calculator, I think it comes out, oh heck, I forgot here. We do our 0.0821, 0.0821 times 500. That number, I gotta square it, times 0.0952. 160. That'd be my value of AP. And again, the big thing to remember is this part, the delta N. Guys, when you go to take your midterm, obviously have these formulas at hand. It's going to be an open book test. You know, we can't stop you from making notes and using them. So you can have notes available. You might want these. I'll be honest, I'm not a big fan of these conversions. I find it to be distracting from the chemistry. But the people who put the course together like these problems in the midterm and the final and the quizzes. Anyway, that's it for equilibrium. Take care.